right, free response question number 5. We're almost home, kids. No calculator, that's all right. An open box is to be constructed from a 10-inch by 16-inch piece of cardboard. This is done by cutting out squares of side lengths x from each of the 4 corners and folding up the sides to form a box. Let's draw a picture. So we have ourselves a rectangle. Yeah. And we're going to cut out 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 squares out of each side. And each square is going to be x in length, x inches long in length. We'll call you 16. We'll call you 10. Now, there's my picture. You're welcome. Explain any domain restrictions for x, the length of the square cut from each corner. How do these restrictions ensure a valid box is formed? Well, basically what's going to happen is you're going to cut out these x's, and the restrictions are basically saying what x values am I allowed to use, right? Like I can't just say, oh no, I'm going to cut 15-inch, I'm going to cut 20-inch x's out of each corner because I don't even have that much information. So what is the smallest possible value that I can use? Well, for A here, the smallest possible value that I could use is 0.00000001. I can cut a tiny, tiny, tiny itty-bitty square and still have enough availability to fold it up and make myself a box with no top. So 0 is my smallest. Now my largest is found by taking the shorter side and halving it, but not equaling that. So if I wanted to, I can cut out sides or squares that are 4.99 and 4.99 and still have just a little bit of space to fold it up and make it the tallest, skinniest box known to man. So my domain restrictions are going to be x has to be in between 0 and 5. And the reasoning why is you must take less than half of the shorter side. Now, why is that? Well, because when you do cut out these squares and fold them up along these invisible lines, you're going to end up, excuse me, I just get so choked up about these problems, I get excited. You end up with a box, okay? The height of that box is x because you're folding it up. You're folding it up. The height of the box is x. The length of the box is found by taking away 2 of these x's. So 16 minus 2x, and the depth, or whatever you want to call it, the width of that box is going to be doing the same thing, 10 minus 2x. We just don't know what x is. Determine the value of x that maximizes the volume of the box. Show all necessary calculations. Well, the way you use it, and by the way, this process is called optimization. The way you maximize or minimize an object is you take the function that can be created. Take the function of what you're trying to find. In this case, we're trying to find the volume. You are going to differentiate that. Take the derivative and find all critical points. You're going to use the critical points and also these points and find out which points are going to give me the largest value. So first things first, I need to come up with a formula for volume. Well, volume of a rectangle is length times width times height. So I'm going to do V equals x times 10 minus 2x times 16 minus 2x. This is just my volume formula. Okay, distribute the x. V is going to equal 10x minus 2x squared times the quantity 16 minus 2x. Okay, FOIL this guy out, FOIL that guy out. So let's be consistent with my colors. 10x times 16 is 160x, so V equals 160 regular x. 10x times negative 2x is negative 20x squared. Negative 2x squared times 16 is negative 32x squared. And negative 2x squared times negative 2x is going to be positive 4x to the third. Let's write this out in standard form and also combine like terms. So 4x to the third will go first. Okay, these guys combine to make negative 52x x squared, and then plus 160x is lingering. Now what I need to do is take the derivative and set it equal to 0. So the derivative of this guy is v prime equals the derivative of 4x cubed is 12x squared. The derivative of negative 52x squared is negative 104x. And then the x just drops away. Oh, 160. See, no one will ever know. Let's move that up here. Set it equal to 0. Now, what I'm going to have to do is I'm going to have to factor that, and I should be able to factor out not a 12, a 4. I can factor a 4 out of that. When I factor a 4, it's still going to leave us with 3x squared minus 26x plus 40. So to find the critical points, we're going to have to continue factoring. This isn't going to get me anywhere. And looking at that, I don't think that's quadratic formula. Nope, it's going to be 3x minus 20 and x minus 2. Right, 3x squared minus 6 minus 20. Yep, so that'll do just fine. That'll do just fine. Now the critical points that I'll get here will be found by taking 3x minus 20, setting it equal to 0, adding 20, and dividing 3, and x is going to equal 20 over 3. Okay? Over here we get x equals 2. Easy peasy. Now at this stage you should be yelling at your phone or computer screen or however you're watching this and say, 20 over 3 is 6.6 repeating, isn't it? Which lands outside of the domain that you're allowed to use, which means you are not an option. You're not. So this is what I have to do. I need to take my endpoints here, and I need to take this critical point here, plug it into the original problem, and see which one of these maximizes the volume. And by doing this, it'll allow me to answer C at the same exact time. So we're going to plug in 0, we're going to plug in 5, and we're going to plug in 2 into this original volume problem. So now I can change colors. Now I feel comfortable changing colors. So V of 0 is going to be, I already know it's going to happen, 0. I'm not going to waste any time doing a whole lot of math. All right. V of 5 is going to be V, so that would be 5 times 10 minus 2 times 5, which is 10, times, you know what, who cares, because 10 minus 10 is 0, so you're going to be 0 anyway. Now we knew this. We knew by plugging in 0, that's me basically saying, I cut out nothing. Now, I know 0 is not allowed, so if we just make believe that this is 0.000000001, I'm going to basically get 0.000000001, and that's not going to be a big volume. Similarly, I know I can't cut out x's of 5, but I can cut out x's of 4.555555555, or 4.999999999, which would be a lot better. And if I plug in 5 and get 0, then plugging in 4.99999999999 is also going to give me 0 or something awfully close to it. So the only one here that's going to make sense is 2. So x equals 2. And how am I supposed to answer this? Determine the value of x that maximizes the volume. So x equals 2 is going to be my guy. So for part C, let's find out why. V of 2 is going to equal, let's use that formula right there, it just seems easier for me, 2 times 10 minus 2 times 2, which is 4, 16 minus 2 times 2, which is 4. That's going to get me 2 times 6 times 12, which is 12 times 12, which is 144. So the answer to part C is going to be 144 inches cubed. All right, so x is 2 inches for B. That's the value that maximizes it. And the maximum volume that we're going to get is 144 inches cubed. So this is the standard box with no top optimization problem. You know, I've been teaching calculus for a few years. I use this problem every year. It's very typical, very standard. Will you definitely see it in an AP Calculus problem or test or whatever? I don't know. But I like it, and so I did it. And that, ladies and gentlemen, is question number 5 for the free response problems. On to the 6, and then we're done.